introduction. And thank you, Dr. Abdul Salim, for inviting me to this FDP, where my guru, Professor Debashish Ghosh, was also part of. I did my PhD under Professor Ghosh. So in that way, I consider this as a proud moment to be part of this FDP. So good morning, very warm good morning to all the participants of the ATAL FDP. So today what I am planning to do is to take you through some basic concepts of robotics so that in the upcoming sessions, you will be able to see in the upcoming sessions, you will be knowing the more details, or you will be diving deep into those subjects later in the upcoming session. So definitely knowing all these that is introductory concepts will help you understand those concepts in a better way. Now, so with permission of all the members, I am sharing my screen. Is the presentation visible?
Yes.
Okay. Thank you. See, being teachers, you will be knowing, right? So if there are no responses from the recipient sides, no, we'll feel no, you are not able to follow. So I request you all to interrupt me as and when required, because no, as it is in Google Meet, I won't be able to see the chat box. So I request you to ask your queries as and when it arises. Okay, so the topic which I am going to cover today is basically the introduction part of robotics. Okay, basically, what is robotics? It is a science of designing and building robots suitable for real-life applications in automated manufacturing and other environments, right? So we need to design and build them. So for that, we have to learn a lot of things. So that is basically the definition for robot. So what comes to your mind when we hear the word robot? Okay, so when we were kids or when we were college-going students, no, first time when we hear the word robot, the picture comes to our mind is that of the robots which we see in films and all, right? So maybe for majority of us, the robot will be a machine which looks like a human being. So is that the case? Always is it like that? Or can we have other types of robots as well? So from layman's perspective, we can define a robot as an electromechanical machine that is guided by a computer program or an electronic circuitry. Okay. So from this is a basic definition. This is not the formal definition of a robot, but to start with, I thought I'll introduce this definition, and let's see which are the different types of robots which we are aware of. So this is a famous concept which all of us have in our mind when we were young, right? The robots are only the ones which are looking like human beings. So this is a famous Honda Asimov robot. So this is another humanoid robot which is developed by another laboratory. And in addition to that, these are also robots, right? Robotic arms or robotic manipulators, they are actually the major, they are actually occupying the major share of robots in industry. So you can see it's like our human arm, right? Robot arm means there'll be a base and some links will be there, joints will be there. Okay, so these class of robots are referred to as robotic manipulators. And these are another class of robots which are called mobile robots. They can be either wheeled or legged robots. Right, so what I'm showing to you are very simple robotic configurations like this. These are differential drive robots, and some advanced robotic configurations like this Pathfinder, where you can see more number of wheels are there. Here also, this is an advanced mobile robotic platform with a manipulator also attached. Okay, so in this case, no, you need to have a coordinated control of all these things, all these configurations. See, because there'll be motors in the wheels, as well as there'll be motors in the links also, this arm also. So coordinated control will be required in this case. So this is another class of robots. And this is a separate class where coming under mobile robots, wherein you could see they are moving on legs. Okay, so they are classified as legged robots. So this is a very, very famous Boston Dynamics robot, which you all might have seen. And this is actually hexapod. So this is also walking on legs, right? And another class is UAVs, that means unmanned aerial vehicles, where you could see these are also classified as aerial robots or flying robots. So that they can be in the miniature form like this, or they can be in the quad rotor form, where there are 4 rotors which are driven by generally BLDC motors. Okay. So if you look at, and there are one more class of robots which are called underwater robots. So, so there are a very wide variety of robotic configurations available nowadays. So through these pictures, what I wish to convey is that we have all these kinds of robots in addition to the typical humanoid robot which were in our minds during our younger days, right? So these are the main class of robots which are available. So among this, can anyone say which robotic configuration? See, if you take the count of robots worldwide, which is leading, can anyone say that among? So I know all are teachers. So so you may be knowing which that is population-wise, which is leading. Can anyone respond to this? Yes, robotic arms. Very good answer. I request Professor Lizzie John to mute her mic. Yeah, thank you. So that's a good answer. So if you look at all these class of robots, see, this is leading because now in manufacturing industries, in process industries, if you look at the automation, all automation has been achieved by means of all these robots. So if you take a total count, around 85% to 90% of robotic population are robotic manipulators or robot arms, which are like our human arms. Okay. So now I move on to the formal definition of a robot. See, this was a very simple definition which I have given what is a robot. But see, according to RIA, this is standard definition by Robotics Industries Association. See, a robot is a reprogrammable, multifunctional manipulator designed to move materials, parts, tools, or specialized devices through variable programmed motions for the performance of variety of tasks. So from the definition itself, we have an idea what is basically, all of us know, right, what is basically a robot, and this definition justifies all those we know. And this word robot has been derived from robota, a Czech word meaning forced laborer. Okay. So in the upcoming sessions, maybe today afternoon, tomorrow, day after tomorrow, you will be taken through some basic concepts of robot transformations, coordinate transformations, robot kinematics, dynamics, robot control, path planning and all, right? So once you go through all these sessions, you'll understand that a little bit of math and all are involved when we have to derive the kinematic model or dynamic model of robots. So basically, I'll tell you why should we learn all those things for actual design of the robots which are beneficial for the society. Okay, so I'll just start with a general trend which we see. Even though we formally are not learning, so many of the students are not learning formally robotics or robotics as a subject. No, our students are coming up with good projects of robotics, right? And see, for example, consider an example of a pick and place robot. Okay, so suppose that robot is used for picking the bottle, a particular bottle from a particular point and placing it at some other point. Okay, so generally what the students does is, okay, from the available motors they have, see, because we need motors for actuation and we need links, so they'll be taking L brackets, C brackets and all, and they will try, okay, whether I'm able to take this bottle from a particular point A. Okay, so what they'll do is by trial and error, they will check. Okay, by trial and error, they will check whether I can take the bottle from here. This is the first attempt, let it be. Okay, this is not working. So then what they'll do is they'll try here. Okay, this is also not working. So they'll try another point. Okay, 3. So when the bottle is kept at this point, okay, the robot is able to pick the bottle. Then they'll fix that. They will say that, okay, this is a start point. They will fix it like this. Okay, this is a start point. Now, suppose what they'll do is by trial and error, they'll move all these motors. So we have these many motors, right? And it will be kept. They will try to keep at this point. Okay, the place point or the goal point. First, they will try to keep it here. Okay, but see, it's not reaching, or they are not able to do that. Maybe then they'll try here some other goal point, G2, and then see, just to have an idea, right? So maybe at G3 they'll be successful and they say that this is the goal point. Okay, and what they demonstrate to us is that, okay, they'll be keeping the bottle at this point and placing the bottle at this particular point, and the claim will be that they have realized a pick and place robot. Okay, so is it that is required for an engineer like us? It's not like that, right? So a customer, as engineers, what we are supposed to do is, suppose an industry is to be automated. Okay, an industry is to be automated and there'll be a conveyor mechanism which is moving maybe like this. So let's suppose this is a conveyor mechanism from where some bottle is to be taken, and there may be some other mechanism where maybe some other arm is kept at this point which has to pick this bottle from here. So maybe this must be the start point and this must be the goal point for a particular application. Then how will you achieve that? After designing the robot, after building this particular robot, I cannot do anything to I cannot do anything to change the start point and goal point simply like that. Okay, or I will just demonstrate with the help of this example. See, suppose the robot end effector has to move through this path. Just imagine. This is a fixed path which is required in a particular industry. Okay, for a particular application, a customer is coming and asking us or the engineer that, okay, I need a robotic manipulator which picks and places or takes object from through these tasks, this path. Or suppose it is to be taken and see, suppose the robot is to pick from this point and place at this point, this particular point itself, okay. So if this is the situation, see, this is given to you, okay, this particular points and all are given to you. So if you try to solve, build without knowing the kinematics or dynamics, you will not be able to do that, okay. So if you have a practical problem before you to do tasks in this way, okay, or the second case, the specific point, see, there is no flexibility in start and goal point, okay, because there will be many robots kept in series for automating a process, right? You cannot simply change the pick and place points. So how will you do that? So definitely you must know kinematics and dynamics, and further like trajectory planning and control, all those things. Then only we'll be able to implement these kinds of applications. Otherwise, what we have to do is by trial and error, we can build, and maybe some approximate start point you can take and approximate goal point you can finalize. Is that what is required as engineers? No, right? As engineers, we should say, yes, I have to take from this particular start point and this particular end point. That is very, very important. And all of us will be aware of another application which we see as being demonstrated by students, right? See, when there will be a line and the robot has to follow a line. So wherever that line is there, the robot will successfully follow that. Can you ever imagine, without drawing a line or a circle, can a robot follow that? So can you just imagine a circle or a straight line which is drawn virtually in front of you where you are right now sitting? Maybe you are at home or you are in your college staff room where, so can you just virtually draw a circle or a straight line and move it through that? So I'll just show you an example where my BTech students have done this project. Sorry. See, so you can see that no circle is drawn, right? But it is following a circle, right? Okay, so can you just imagine a circle like that near your staff room or wherever the project is being taken up, and there is no line drawn and still the robot is following a circle? How that can be achieved? Without knowing kinematics and dynamics, you won't be able to do that. Okay, so that is why we should know, see all these things. And sometimes another example which I have seen generally done by students is they'll say, okay, I have built an obstacle avoidance robot. Okay, so what this robot does is, it does is, okay, maybe there will be a start point here. Okay, this is a start point A, and there'll be a start point A, and there'll be a goal point B. They will not think about the goal point at all. See, generally, why should we see the robots should be used for some particular application, right? And what the students does is, okay, the robot will be moving forward straight line like this. When an obstacle is encountered, what their algorithm does is turn right, turn left, khatam. And then there is no where should the robot go? That is not at all mentioned in the report. Okay, so you cannot claim this as an obstacle avoidance robot. So it will be just wandering like that, right? So always when we look at these kinds of problem, you should always think of a start point. Okay, so always we do like that, right? So suppose a robot is being used for distributing food packets to the COVID affected patients in a hospital, right? So if you are employing a particular a robot like this, or a bigger version of a differential drive robot you will be able to use. So if we are using that, if this obstacle avoidance algorithm is used, how it will reach the destination? It will not reach the destination, right? It will just take a left turn or right turn, and then maybe again take a right turn or left turn whenever then obstacles. So it should not happen. So what it should does is, see, it should avoid the obstacle, and then it should go back to it should reach the destination part which is given here. So whenever we are asking our students, to come up with projects, so we need to say, okay, we should not just encourage students by saying that, okay, it should take a right turn or left turn. It should be moving to a goal point, and while avoiding obstacle, it should be able to reach the destination like this. See, if you look at this is a scenario. All these, from goal point to end point, avoiding obstacles, it is moving, right? So in this way, we should be able to design robots capable of doing all these tasks. See, whenever we employ a robot for a scenario like a hospital, which I was mentioning, because nowadays, robots are really helpful in distributing medicines and food packets to COVID affected patients, whom are being admitted in different rooms, right? They'll be admitted in pay wards to different rooms. They have to be, the food is to be delivered. So while the robot is moving, it may have to encounter obstacles and all. So definitely all these should be kept in mind. So why I have shown these three examples is that only if we know the kinematics, the dynamics, trajectory planning, the robot control and all, we'll be able to come up with these kinds of projects which are helpful for the society. So who all will be able to contribute in robotics? See, basically, robotics is an interdisciplinary area which include many engineering disciplines: mechanical, electrical, electronics, computer science, etc. So if you are a mechanical engineer, you concentrate more on the design part because you will be an expert of that. So more on the design. So suppose if there is a wheelchair and the wheelchair is to be moved through a stair, okay, maybe a stair climbing wheelchair, okay. So if you think of that application, so definitely a mechanical engineer will be able to help us in the mechanical design part, because they are very good in that part. So where the mechanical engineer can contribute, but the same wheelchair or stair climbing wheelchair, the control part integration can be done by electrical engineers. If there are sensors and all, both electrical and electronics engineers will be able to do that. And depending on the applications, right? So if camera is involved, a lot of image processing is involved, electronics, sensor fusion and all are involved, electronics engineers can contribute. And computer engineers or computer science engineers can contribute in development of optimal algorithms for implementing or realizing all these robots. So all these people will be able to contribute in one way or nowadays, I think the title of the course is also Robotics and AI, right? So a lot of people are nowadays working in AI part also. So you don't have to be master of all these in order to work in the area of robotics. Whichever area is comfortable for you, you will be able to work on that and come up with very useful contributions. Okay, so robotics has achieved its great success to date in the world of industrial manufacturing, and it is assumed that between 2018 and 21, almost 2.1 million new industrial robots will be installed in factories around the world. Okay, so that is the statistics if you look at. And the evolution of robots means, see, it all started in 1960s, if you look at this picture. But the initial robots were also the industrial robots, but later, maybe you can see in 1968, see mobile robots and slightly walking robots and all have been developed, and then came the humanoid robots. And in recent years, see, if you look at this 1995, 2005, so that is where the service robots have found more importance, wherein many of our researchers are working in these areas, wherein see exploratory robots, office or tour guide robots, surveillance robots, domestic robots. A lot of research has been happening in the service robot sector nowadays. And suppose if you look at the industrial robot sector, the type of contributions or research contributions are kind of saturated, and nowadays what we could see is many are concentrating on this area for their research. So now I'll be just taking you through some basic concepts of robotic manipulators, okay, because which is that's population wise that is leading. So if you consider a robotic arm, it is similar to that of human upper limbs. Okay, so if this is actually referred to as an open kinematic chain. Open kinematic chain means one end is fixed and the other end is moving. Okay, so there are robots wherein this end is also fixed, which are called parallel manipulators or closed kinematic chains. That is a different class of robots. An example is called as Steward platform is an example of a closed kinematic chain. So that's a different class of robots. I have not included that in this presentation. So this is basically an open kinematic chain of rigid links. So you could see links. So these are called links interconnected by joints. So these are called joints. Okay, you could see these are the joints. Okay, and this part is called the end effector. Okay, where that is interaction with the world is happening. So that is the end effector part. So you can see a gripper at this end as well as in this end. So if you look at a standard robotic manipulator, these are the main parts. There'll be links, joints, and other structural elements for interconnecting them. And end effector, I have shown it's a part connected to the last joint of the manipulator. It handles objects and it performs required tasks. And actuators are, what are the actuators of human beings? See how we are able to pick and place an object using our hand. What are the actuators of human beings? Muscles are the actuators of human beings, right? Because it causes movements or motion. It helps movement of our body parts, right? So these actuators are called muscles of manipulators. So examples are commonly used servomotors, stepper motors, and hydraulic or pneumatic actuators or cylinders have also been used as actuators. So as an engineer, suppose if you are asked to build a robotic manipulator, so you should know the characteristics of all these actuator mechanisms. Then only you will be able to choose, okay, which one I have to use. So suppose you might have seen, at least in videos, robots are being employed in manufacturing industries, right? So which actuator can be used in a car manufacturing industry? Suppose you have a robotic arm manipulator like this, which is used for picking and placing a car. Okay, there'll be two robots maybe side by side. It will be assembling different parts to the parts of the car to see in place. So which actuator can be used among this? If you use a robot in a car manufacturing industry. Can anyone tell me? Any answers I wish to see? Any suggestions? Yes, hydraulic, that's a good answer. So hydraulic actuators are used if we use for robotic manipulators in car manufacturing industries, we use hydraulic actuators. So you should know the characteristics, because for heavy payload, for manipulating heavy payload, hydraulic actuators are the best. Okay, but suppose if it is a food processing industry, okay, and suppose if it's a food processing industry, you cannot use hydraulic actuators, because hydraulic actuator means it is an actuation based on the force from oil, right? So you cannot use that in food processing industry, because the main disadvantage of hydraulic actuators is that it leaks. The cleanliness is the main problem associated with that. So you will not go for hydraulic actuators in a food processing industry. Rather, you will go for a pneumatic actuator, because the actuation mechanism is air. It's available in plenty. The speed of operation is very good, right? The only problem is that if there is leakage, it can lead to efficiency problems. So it all depends. Only if you know, right, okay, what are the plus points and minus points, and how is its characteristics, you will be able to employ a particular actuator for the robotic arm. Even for automating industries, you need to know, okay, how much payload it is able to handle, whether it is fast, whether it is able to meeting our requirements, and based on that only you will be able to choose the actuators. Okay, then comes sensors. Okay, so sensors, when we have to make it autonomous, without sensors, we won't be able to do that. So collect information about the internal state of the robot. So the main sensor which gives internal information, internal state of the robot, will be the encoders, the position encoders, which are sitting at the joints, which will help us in getting, okay, how much angle the robots have moved. And maybe outside we can use camera sensors, and sometimes we can use touch sensors, sonar, IR. So these are mainly used in mobile robots. Okay, light sensors and all. So mainly internal sensors, for manipulators are basically position velocity encoders, and sometimes when there is interaction with the environments. For example, suppose you need to, after writing in the blackboard, that is to be clean, the blackboard is to be clean. Suppose just you imagine a duster is attached to the manipulator and just cleaning the blackboard. So then what happens? There is interaction with the environment. Okay, so then you need to have force sensors or torque sensors which are attached to the robot in order to know that, okay, how much interaction forces are coming, and accordingly the torques are to be given to the joint. So these are that types of, so if you have to make a robot autonomous, all these sensors will be required, and definitely the brain part of any robotic arm will be the controller, which controls the motion. So depending on the requirement, the ruggedness of the controller, you can choose the required controllers. And so as I was mentioning earlier, if you look at the main parts of a robot, so I'm just mentioning about the basic joints, which are, there are other advanced joint configurations. So the common joints are revolute joints and prismatic joints. So revolute means, see, with respect to this, the second joint, see, these are the links. So this is the first link, this is the second link. So when this rotates, this joint rotates, this is moving, this is rotating about this axis. So this is called a revolute joint. So if you take the joints in a human arm, so if you extend your arm, okay, can you just check whether our joints are revolute or prismatic? See, all our joints are revolute in nature because we can rotate alone. There is no possibility of extension like this. So prismatic means it is sliding. So there will be a fixed link. There will be a sliding link like this. So there is a linear motion in this way. So that is called a prismatic joint. And next important point we should know is work envelope of a robot. Okay, so work envelope means the locus of points in 3D space where the end effector can reach. Okay, so that is very, very important because see, it's a customer who comes to you and asking, okay, sir, so and so I have this. I'm actually having this industry. I'm planning to automate this. It's okay to use robots and all. So it's as engineers who have to decide, okay, which robotic configuration is to be used. So it's very important to know what is a work envelope of a robot. Okay, so work envelope means work envelope is decided by the first 3 axes of the robotic arm, which are called major axis, and the remaining joints are actually the first 3 axes determines what is the work envelope of a robot. Okay, so see, geometry of work envelope is determined by the sequence of joints used for first 3 axes. Okay, so so that means, see, these are the famous robotic configurations. See, so that's why I was telling you, it's kind of saturated. The robotic configurations, all those things are readily available to us. It's just a matter of employing them in the manufacturing industries. Okay, so this is the very basic configuration, which is called a Cartesian robot. Okay, Cartesian robot means all the joints are moving linearly. See, look at this. See, this is moving in this direction, like this as well as this. See, this is back and forth. The second joint or the second link is moving like this, to and fro, and this is also up and down. Okay, so that means there are 3 joints which are moving linearly. So that means if you look at these type of joints, the configuration is prismatic joint. Okay, so I can say that if you take a Cartesian robot, the joints are prismatic, prismatic, prismatic. We call it as PPP configuration, which is a very basic configuration, and it's also referred to as a rectangular robot. It's also referred to as a rectangular robot. See, if you are employing this kind of robot, the work envelope you are going to get is going to be a rectangular box like this. Okay, so suppose if you see the work envelope required for a particular task is within this box, we can go for this basic configuration, which is a rectangular robotic configuration. Okay, so sometimes that may not be the case. Okay, sometimes the application demands that we need a cylindrical configuration like this. Okay, so see, this is actually a cylindrical robot wherein you could see the first joint is revolute, second joint is prismatic, and third joint is prismatic. Okay, so the configuration is RPP. Okay, so if you use RPP configuration, we call that as a cylindrical robot, and the work envelope which is generated is cylindrical in nature. Okay, and if you have a little more advanced configuration, which is RRP, which is revolute prismatic configuration, then you will get a spherical work envelope. So you won't be getting full sphere because it will be placed in a table. Maybe you will be getting a hemisphere actually, based on the setting where you have mounted the base of the robotic arm. So you will be getting a configuration work envelope like this. So the end effector can be moved anywhere inside this, okay, inside this. So this is actually called RRP configuration. And the last configuration is actually the most complex work envelope and the realistic configuration, like a human arm, which is called an articulated robot. Articulated means human, most anthropomorphic in nature, means most human-like. Okay, so it is revolute. So this is more realistic work envelope. So if you have, if you need, so depending on the application, right? Depending on the application, we may have to choose. So this is PPP, this is RPP, and this is RRP, and this is RRR configuration. Famous robotic configurations which are used in manufacturing industries. So if you see, depending on the requirements, see, so that is why I was telling that the work envelope is very, very important. So depending on the application, you have to choose, okay, whether I need this work envelope. So work envelope means inside this point, any point within this work envelope, then end effector will be able to reach. Okay, so and see, if you know all these configurations, okay, you can decide, okay, this is the kind of process which I have to automate. Okay, so the process will be starting from step A, then B, C, like that. Okay, from step A point, so initial point, which robot I have to implement. That is whether symbol configuration like this is fine. See, if there are no obstacles and all, this is okay. Okay, so perfect work envelope and all you will get like this. So depending on the application, you have to use these configurations. And there is a famous configuration, I forgot to include that slide, which is called SCARA robot. Actually, SCARA, which is a very famous robotic configuration, which is called Selective Compliance Assembly Robot Arm. That is also a very famous robotic configuration, which is a cylindrical robotic configuration, which is, even though the robotic configuration is RRP, but you will be getting a cylindrical configuration because of the construction of the robot mechanism. Okay, so maybe as a robot enthusiast, you can just have a look at SCARA robot configuration also. And Puma is a very famous configuration, which is a 6-axis robotic configuration, which is a see, all these robotic configuration we have considered only the first 3 axes. See, the first 3 axes determines what is the work envelope, and see, the remaining joints are referred to as the minor axes. Okay, so the importance of minor axis comes, so for maybe for demonstrating that, I will be just switching on my video. Hope you can see. See, suppose I have this is my mobile phone, so I have to place this mobile phone, maybe from a table particular point I have to take and place it at some point. Okay, for example, suppose this is the destination point where I have to keep the mobile phone. Okay, so maybe initially the robot is the mobile phone is at this point, and it has to be kept at this point. Okay, so if you look at this configuration, see, if you look at this particular point, this is the position of the robot. Okay, so if you take the CG of this mobile phone, so I will be feeding the CG of this mobile phone to the manipulator, and the manipulator will be keeping my mobile phone like this. So suppose if you have to keep the mobile phone only at this particular configuration, the 3 degrees of freedom is fine. Okay, but sometimes no, you may have to see, you may have to achieve a configuration like this. See, this is see, same position. So if you look at XYZ of the CG, it is same, but see, the orientation is different. This is another orientation. This is another orientation. Okay, maybe when we use this for different application, maybe we have to insert a disk to some other place. Okay, maybe we have to hold this at 45 degree, right? So in that scenario, the orientation is also very important, right? So if orientation is also to be manipulated, we need more than 3 degrees of freedom. So you are worried only about the positioning. Okay, just X, Y, Z coordinate you give, and there you need to position the object. Then no, 3 degree of freedom is fine. But when orientation also matters, then you have to go for higher degrees of freedom. So that will help you in achieving more. We call as dexterous work envelope, or more realistic work envelope you can achieve if you use minor axis. So that means, see, we have robots for 5-axis robots, 6-axis robots and all. So you will be getting, you will be able to move around obstacles, and you will be able to do any task as and when required. Okay, so next terminology related to robotics is called degrees of freedom. Okay, degrees of freedom means the number of independent movements that an object can perform in 3D space. Okay, so that means if you have 6 degree of freedom robot, you will be able to achieve any position as well as orientation in 3D space. Okay, and if you need more dexterity, you have to use more than 6 degree of freedom. And if the degrees of freedom is more than 6, we call that manipulator as a redundant manipulator. Okay, so this is basically human arm-like mechanism, which is comparing the shoulder, elbow, and the forearm. Okay, so basically all robotic manipulators are very much similar to human arm. Okay, not all manipulators, basically the ones with the revolute joints are similar to that. So if you look at, see how blessed we are, so that we will understand when we look at the degrees of freedom we have for our human arm, right? So what is the degree of freedom of elbow? Can anyone say? What is the degree of freedom of elbow? How many degrees of freedom elbow has? 2. Which are 2? 2 or 1? How many directions you can? Yes. So because you can move in only one direction, right? Maybe the other direction, it is achieved by the shoulder joint, right? Basically it is. And what about shoulder? How many degrees of freedom?
3.
Yes, shoulder has more degrees of freedom. And what about wrist?
2, madam.
Yes.
Is it?
Yes,
I guess
yes.
it is 2.
2. Yes. Yes. So see, this is how. So this just illustrates how blessed we are. See, so many degrees of freedom we have. So when we try to realize or design a robotic manipulator with all these degrees of freedom, we'll understand the difficulty. Okay, we start with the kinematic model, and then if more payload is to be taken, then we go for a dynamic model. So all those are going to be complex when we take our own arm. Okay, so we need to know. Okay, so for a particular application, we need to know whether how many degrees of freedom are required, whether only position information is to be shown, or position information is to be achieved, or different orientations are to be achieved. And depending on that, we will choose how many degrees of freedom the robot needs. And in robotics, one of the important topics which we'll be learning is coordinate transformations. Okay, so coordinate transformation is to model the motion of robot arm. Coordinate frames are attached to various parts of the arm. And what we'll be doing is right-handed orthonormal coordinate frames are attached. So right-handed orthonormal coordinate frames I'll be showing you. See, it is this is what is right-handed orthonormal coordinate frames like this are attached to robotic arms. Okay, so what we do is generally, so you might be knowing the analysis of different systems. Like suppose if you are asked to model an electric motor, all of you know, right, how to do that. And suppose if I ask you to model an electric vehicle or another autonomous car, you know how to model that. But when we consider a robotic arm, there is some difference. Okay, unlike a car moving on a road or what can I say, or some other machine moving, or a mobile robot moving in a floor. So if you consider a human arm or a robotic arm, the analysis of movement is little bit complex. So why it is complex? See, suppose, see, when I am moving this mobile from this particular point to this particular point, just imagine which all joints are moving. Okay, at a time, see, maybe my shoulder is moving, my elbow is moving, maybe my wrist is also moving. Okay, for example, just imagine shoulder joint is locked at a particular angle. So you can just imagine some angle theta1, just imagine at particular angle shoulder is locked, and particular angle elbow is also locked. And then by, see, suppose if it is like this, you see, you can just move the wrist, right? Move the wrist like this. Okay, so if only the wrist is moving, no, then okay, we can analyze. But the thing is that when the wrist is moving to pick and place an object, at the same time the elbow is moving, the shoulder is moving. So how to model see these all simultaneous movements together? So that is why we are going for coordinate transformations. Okay, so that is what is that is why these coordinate transformations are required. So what we do is to see right-handed orthonormal coordinate frames are attached, and to transform the coordinates of a point with respect to one frame into coordinates of with respect to another frame. So that is how we'll be proceeding. So what we have to do is, so we'll be having one, see, suppose you have a two-link arm like this. Okay, so suppose you have a two-link arm like this. In frame assignment, what we do is, first we'll be assigning a frame like this. Maybe this is X, this is Y, and this is Z. Okay, one frame I'll assign. Maybe that is the base frame, we'll say. Okay, so we'll be assigning one more frame which is at the joints, at the joint. So all those things you'll be studying in the session on kinematics, but I am just telling you in a very approximate manner. So just imagine you assign a frame here, you'll be assigning another frame here, another one at the end effector. So, okay, so there are some assumptions for in which way these frames are to be assigned. So that algorithm is called DH algorithm. Okay, DH algorithm, or we call as Dennavit-Hartenberg algorithm, helps us in assigning these frames. So what we do is, we'll be assigning these frames, and what we do is we will be trying to find what is the position and orientation of this particular frame with respect to this, then this particular frame with respect to this. Okay, so then what we do is, see, suppose this transformation, so we call, suppose this is frame 0. So just imagine this is frame 0, let it be frame 0, let L0 I am marking, this is L1 and this is L2. What we do is we'll be trying to find a transformation T10, that is from the first frame to the base frame, and then from 2 to 1. Okay, so we have to find these transformations independently, and then we'll multiply that and we'll find a transformation called a T20, which indicates the position and orientation, of the end effector with respect to the base. Okay, so this coordinate transformations will help you in knowing the position and orientation of the end effector with respect to base. Okay, so you need to know all these things. Suppose if you wish to design a particular robot for a particular applications. Okay, so ultimately we'll be finding T-tool base in this coordinate transformations. So all those things will be discussed in detail in the upcoming session. So I was just giving you an idea. Okay. And next common terminology, if you are expert in robotics, is that you should know what is called kinematics. Okay, kinematics and dynamics. So kinematics means it is the analytic study of geometric motion of robot arm with respect to a reference frame without regard to forces and moments that cause the motion. Okay, so we have to study the movement of the robotic arm or even a mobile robot without considering forces and moments. So that is called as kinematics. And suppose if you have, and suppose, see, if you consider kinematics, there are actually two types you need to learn. One is called direct kinematics and second one is called inverse kinematics. So direct kinematics means you will be given, okay, direct kinematics means you will be given the joint angles. See, this is theta1. So this is a two-link manipulator. So theta1 is known, theta2 is known, and the link length is available. Knowing or finding out the end effector position is called direct kinematics or forward kinematics. Okay, and inverse kinematics means you know the end effector position. Finding theta1 and theta2 are called inverse kinematics. Okay, so direct kinematics, no, it is easy to solve, but inverse kinematics means there can be multiple solutions for inverse kinematics problem. So multiple solutions means you will be able to achieve the same end effector position by in multiple ways. For example, see, I have not included that diagram. I'll just show you. Okay. For example, suppose there is a two-link manipulator, three-link manipulator. Just imagine this is a base. This is a base, and this is the first joint and first link. Okay, let this be the first link. This is second joint, second link. Let this be the third joint, and this is the end effector. For example, just imagine this is the end effector. Okay, so if you consider, let me take another color. Suppose this is the end effector position. Let that position be pxy. Okay, which is xy, p is equal to x and y. Suppose we say that, see, what is inverse kinematics? Inverse kinematics means you know the end effector position, finding the joint angles theta1, maybe theta2, and this is maybe theta3, whatever, in whichever axis you mark, this is theta3. So this is first solution. So you have the first solution, theta1, theta2, theta3. Okay. Suppose if the robot is kept in this way. See, In this way also I can keep, right? So I am, see in this, if I keep the robot like this, then also end effector position is Pxy itself. But what is the solution? The inverse kinematics, theta 1 is different. Theta 2 is different, right? So this is what is called a multiple solution. For the same end effector position, you can have different joint angles. Okay, so in that way, solving inverse kinematics problem is slightly difficult because now from the multiple solutions, you have to find the most suitable solution. Okay, but direct kinematics means you will be getting the correct end effector position and orientation as a single 4x. See, solving the direct kinematics problem means you will be getting a matrix T tool base, which is equal to, which is a 4x4 matrix with this as, we call this as rotation. This is position. And this is perspective. And this is scaling factor. So what it means is that if you will be having a 4x4 matrix where you will be having orientation information. You will get orientation information from here, position information from here. If there is camera, perspective information from here, otherwise this part is 0 and scaling factor is generally 1. So this 4x4 matrix will give you what is the position and orientation of the end effector with respect to the base. Okay. So, by solving forward kinematics, you will be getting that 4x4 matrix. Okay. So I have also mentioned about a terminology which is called dynamics. Dynamics means we'll be considering forces also. Okay. So in which context we go for kinematics and in which context we go for dynamics. So as far as manipulators are concerned, if the manipulator is moving very slowly and the payload to be managed is very less in grams or so, then no, you can just start with kinematic model, and then no, if you take the Jacobian and all, no, you will get the joint velocity and end effector velocity relations, and you will be able to design a robotic manipulator. But imagine that the robot has to take a very heavy payload, 5 kg, 10 kg payload. Then no, you, without knowing dynamics, you will not be able to exactly design the robotic manipulator. So that is why we should know kinematics and dynamics. So from a different perspective, I can also say that, for example, for the example of because no, it's a COVID time. That's why I am mentioning the examples of a robot which is being employed for helping COVID patients. For example, suppose you are designing a robot which is to be deployed in a hospital for supplying food to the patients. Okay, so just imagine like that. So in that case, suppose food packets, suppose there are 25 food packets are to be stacked in the mobile robot. So then there's a very good possibility that the payload is very high. Okay, so there'll be 6-7 kg of payload in the robot which is being used. Okay, so then it is good to model, get the dynamic model of the robot and then proceed. But suppose you are designing a robot just to roam around and announce that, okay, you should follow social distancing, use sanitizer, just announcement, randomly it is moving. It is not having any payload, just imagine. Okay, so if payload is too less, no, you can just use the kinematic model, so that you need to just give the left wheel velocity and right wheel velocity as control inputs, so that the robot will be successfully roaming around and distributing medicines to the patients. But the thing is that if for example, the food packets are to be distributed, it is better to compute what is the torque at left wheel and what is the torque at right wheel, so that this robot will be able to deliver the medicine or food from one particular point to the different rooms assigned to that. Okay, so that is the necessity of knowing kinematics and dynamics. Okay, without that, trial and error you can do. But so I always strongly believe that being engineers, we should always rely on engineering solutions rather than trial and error solutions. So that is why you need to keep in mind that when payload is involved, we should try to find the dynamic model and then try to find the torques required at the joints, or in the case of mobile robots, torques for left wheel and right wheel. So these parameters and all are required, which called a link length, link twist, joint angle, joint distance. All these are required for finding the forward kinematic model. So all those things you will be studying later. So I was just setting up a foundation, right? Okay, why should we learn all these things so that we'll be able to successfully design a robot for supporting the society. See, ultimately, this is what we do. See, the frames are attached depending on, so these frames are attached based on Danawit-Hartenberg assumption. So these frames are to be assigned and coordinate transformations are to be found. So there is something called a link parameter table. So that is to be written in order to find the end effector position and orientation with respect to base. Ultimately, when you solve that, you will be getting a 4x4 matrix, 4x4 matrix like this. So there'll be some values. This is a 3x3 matrix. So this will be 3x1. Okay. So this is generally 0 and this is 1. Okay. So based on these values, you can say, okay, what is the end effector position as well as orientation. Okay. So this is what ultimately the for kinematics, forward kinematics does. Okay. Once you do that, you will be able to see always know. Before designing, we need to know the model so that then only we'll be able to implement them successfully depending on the customer requirements. So next terminology which you may hear in the upcoming sessions is trajectory planning. See, the goal of trajectory planning is to describe requisite motion of this manipulator as a time sequence of joint or link or end effector locations or antiderivative location. So that means suppose you have a 3-link manipulator. Just imagine you have a 3-link manipulator. Okay, so 3-link manipulator. Trajectory planning means, for example, suppose the end effector has to move like this. This is an arc. This is the end effector. Maybe, for example, just I am telling you, the end effector has to move, take a path like this. If that is the case, trajectory planning means what is θ1 of t? What is θ2 of t? And what is θ3 of t? That is what is referred to as trajectory planning. Okay, so that is what is written here as a time sequence of joint or link or end effector locations. So generally what we take is a sequence of joint locations we will be taking. So that is what is written as θ1t, θ2t, θ3t. So how to find that? Okay, so if the end effector path is to be like this, we'll be able to compute that, and you need to, it's just a matter of driving the joints θ1 through this profile, θ2 through this profile, and θ3 through this profile, so that the robot end effector will do the required task of moving through this arc. Okay, so when we are computing this path, one thing we have to keep in mind is that the trajectory, that is theta 1 t, theta 2 t, theta 3 t, should be smooth. Okay, you cannot have jerks in robotic manipulators. So we need to make sure that the path is smooth. So the famous trajectory planning method is called the cubical polynomial path planning method, wherein the third order polynomial is being assumed as a path for joins, so that it will be having, we'll be able to take multiple derivatives, and the path followed by the manipulator will be smooth. Okay, so see, in addition to this position, we may require sometimes theta 1 dot of t. So that is what is written as derivative of locations, theta 2 dot of t or theta 3 dot of t, because the speed at which this robot moves are very, very important, especially in pick and place tasks. For example, see, suppose you are, suppose if you are implementing a robot for pick and place task, suppose if this is a pick point, okay, if this is a pick point, and this is a place point, just imagine this is a place point. Okay, so when suppose robotic arm will be coming here to pick the object, right? So what happens is until it reaches a point near to this, it will be moving fast. Okay, it will be moving fast to up to this point. Then it will be moving very slowly up to this, and then it will be picking. Then up to this, see, it will come down, end effector will come down, pick the object. Slowly it will move up to this point. But here, even though it is moving fast, in this way also it can move fast. In this way also it can move fast. And up to just before the place point. So if you find another point here, just before the place point, it has to say up to this point, it can move fast. But while we have to place it, it has to be moved very slowly. Okay, so that is why the derivative of locations are also important. So that is why see, theta 1 dot t, theta 2 dot t, theta 3 dot t are very, very important, because see, even if we consider the pick and place task, see, just near the pick point and just near the place point, the velocities are less. So these are all very important, right? So, but here we can have higher velocities. So even though the velocities are higher, it won't be a problem. So the same situation we might have experienced when we are moving in lift. Okay, so when we just suppose from ground floor we are going to third floor. Okay, so just we get into the lift. When the lift starts, it will be moving slowly. But after something, it accelerates. Then towards, that is when the lift is about to reach the third floor, it decelerates slowly. And so that is actually this part. Okay, so then slowly it stops. So in a similar way, for pick and place task also, this velocity profile is to be followed. Otherwise, there can be, this can hit the object. Or here also this can hit the workbench and all. So that is not desirable, right? So when we are planning the trajectory, these points are also, we have to keep in mind. So this is a typical block diagram for trajectory planning. So we'll be given the kinematic model, the dynamic constraints, the path constraints, because there can be some obstacles or in between. So the path specifications will be given, and based on the constraints, we need to get the time sequence of points with location, velocity, and acceleration. So that means actually, if it is planned in joint space, you will be getting theta dot and theta double dot profiles. So knowing this is referred to as the trajectory planning. Okay, so if you have this, you can just control the robots to follow this path. And the last topic which I will be mentioning today is about robot control. So once a nominal trajectory is planned, the problem of issuing commands to the joint actuators that will cause a manipulator to faithfully track or follow the planned trajectory is called a robot control problem. So once, see, it is actually a systematic way of implementing a robot. So first you need a kinematic model, and suppose payload is less, then it's fine. You can directly go for trajectory, and then you have to find the Jacobian matrix, and in order to get the join velocity and the end effector velocity relations, and then the trajectory planning, and then the directly robot control. But if its payload is more, you have to kinematic model, dynamic model, trajectory planning, and then comes the robot control. Okay, so if the manipulator moves very slowly or move one joint at a time, then control is very simple, because coupled dynamic forces will be negligible. There are some assumptions in robot control wherein we can use single axis PID control. So there are the assumptions that only one joint is moving at a time and the robot arm is moving slowly. But if it is moving fast and it's having payload, higher payload, it's better to go for non-linear control methods like computer torque control or so. So otherwise, we can use a very simple single axis PID control or PD gravity control. So because for gravity compensation terms. So this is a typical block diagram of robot control. So it's like a typical control system block diagram. So instead of another dynamic system, we have a robotic manipulator or even a mobile robot, whatever we have, that is represented in this block. So you can see that the feedback is taken, the position and the derivative of position. So that is, if it is a robotic manipulator, it will be the position and velocity, and we will be having sensors which gives so generally in robotics we'll be representing these position as q, as generalized coordinates, q dot and q double dot. So that is sensed, and that will be fed to the manipulator control system. So already we know how to find the trajectory, how to compute the trajectory using the trajectory planner. So from the decide task and position, decide task, so that will be the position and orientation of the end effector, right? So that will be given to the trajectory planner, and the trajectory planner will be finding or computing what is q dot and q double dot required, and that is fed to the manipulator control system. And we know what is the actual q and q dot, and that will be compared, and based on the error, this manipulator control system will be correcting or moving the manipulator in the required path. Okay, so that's a typical robot control block diagram. So that's all. So see, based on the type of system, so see, suppose if you are assuming that only one joint is moving at a time, and the robot is moving very slowly, the linear controllers might be okay, but otherwise we may have to use non-linear controllers. Okay.
গরম ঠান্ডা কি বলছিলেন? হ্যাঁ, যেটা বলছিলাম আপনাকে কিরকম হচ্ছে শীতকালীন ধরুন আমরা কোন কি লাগিয়েছিস কন্ট্রোলার, সিম্পল পিআই কন্ট্রোলার। আচ্ছা, শুধু পিআই কন্ট্রোলার দেখছি। হ্যাঁ, এটা আমি সিম্পল পিআই কন্ট্রোলার দেখছি। কিরকম ভাবে করেছি আপনাকে বলি। ধরুন এই যে ইকুয়েশন,
I request Mr. Arvind Kumar Pal to mute the mic.
Okay.
Okay. So so that's all from my side. So I request the participants, if you are having any doubts.
Thank you, Diksha madam. It was a very nice presentation, and participants, you can join the discussion if you have any doubt.
I have one doubt. Can I
Yes,
ask?
please. Yes, please. Yes, please.
Okay, you are told about this T toolbar now. So that is 4x4 matrix. Is it 4x4 matrix always or any
Yes,
different?
see, if we consider rotations alone, it is 3x3 matrix. But coordinate transformation matrices are always 4x4 matrix, because we need to represent orientation, which is 3x3 matrix. Rotation part is 3x3. Actually, for position, we need 3x1 only. But no, when we use a 3x3 matrix for rotation and 3x1 matrix for position, it will be actually 3x4, which is not a square matrix. So that is why we have a perspective and scaling factor ultimately, which will yield a 4x4 matrix.
Okay, what is the meaning of this perspective? It is given as 0, 0, 0. Why it
Yes,
is?
yes. Yeah, it is given that is when we are using camera in the workspace, that will be actually having non-zero values. So how that is computed? So there are some steps involved in doing that. So generally, if camera is not used in the system, we'll be taking that as 0. If camera is used based on the camera arrangement, so there'll be you should know what is the focal length of the camera, so where it is kept. So based on all those things, that values will be having non-zero values. Otherwise, those terms will be non-zero values. Otherwise, yeah. So
Thank you.
Hello, madam. Good morning.
good morning.
So my name is Tennyson Gajos, and I am from GEC Thrissur. So I have a doubt. How we can fix that the major axis and minor axis? Is there any rule for it, or we are simply taking the x, y, z as the major axis?
No, major axis means first 3 axes from the base. See, first we'll be fixing the robotic manipulator at some point, right?
Okay.
So from that joint, first 3 joints are referred to as the major axis.
Okay, madam.
Okay, so that will determine what is going to be the work envelope.
Okay, that's fine. Okay.
Yeah.
Okay, ma'am. Thank you.
Any other queries? Okay. Now I request Safina for the concluding remarks.
A warm good afternoon to everyone. We were having a presentation on Introduction to Topics by Dr. JIsha VR, Associate Professor, CET Trivandrum, for the past few minutes. And she has given a very good description on robotics, the different types of robots, parts, and she has given a familiarization of the different robotic configurations. Also, the importance of understanding the kinematics and dynamics of robotics while designing. She has mentioned the importance. Thank you, ma'am. Thank you very much, ma'am, for your wonderful presentation. On behalf of Department of Electrical Engineering and coordinators of the FDP, I express my sincere thanks to Dr. JIsha VR for giving such a simple presentation which everyone can understand. I also thank the coordinators for bringing such eminent persons for conducting this FDP. Thank you. Thank you once again.
Thank you all once again. Thank you, Professor Meenakshi, for the nice words. Thank you all. Happy to be part of the team once again.
Okay, thank you everyone. Thank you, JIsha madam. Okay. And we will be meeting again at 1:30 p.m. You can mark your attendance by filling the Google form that is linked now, that is shared now.